All right, welcome to the deep dive. Today, we're going to be jumping headfirst into a subject that you, our listener, have clearly been spending a lot of time with, and that's machine learning.
Yeah, it seems like you've really been hitting the books hard.
You've shared a whole stack of your study notes with us.
And it looks like they span several weeks.
Yeah, so we're going to try to condense all that knowledge, all those insights.
Into something a little bit more digestible, right?
Yeah, into something that will really help you connect the dots and get to those aha moments.
And save you some time, right? So you don't have to wade through all these pages and pages of notes.
Absolutely, yeah. So specifically, you've been digging deep into MLT Summary Notes.pdf.
That's right. That's the file.
Which covers a pretty wide range of machine learning topics.
Yeah, it really does. It starts off with dimensionality reduction.
Right, like PCA.
That's principal component analysis, exactly.
Kernel PCA as well.
That's right. Then it jumps into clustering.
K-means.
K-means, exactly.
Then it goes into estimation.
Which uses methods like maximum likelihood estimation and Bayesian approaches. MLE, right?
And Bayesian approaches.
And then from there, it dives into, some of the really core algorithms.
Like linear regression.
Linear regression, that's right. You've also got stuff in there on overfitting.
Regularization, right, to prevent overfit.
Exactly, and how they're tied together.
And then even more algorithms, too.
Yeah, so we've got linear and kernel regression, linear classifiers, like perceptron, KNN, decision trees.
Generative models.
Things like naive Bayes and LDA.
And then finally,
support vector machines.
SVMs.
SVMs, right?
Logistic regression.
So you really covered the whole gamut here.
Yeah, it's quite impressive. And it's clear that you're serious about mastering machine learning.
Yeah, you're really trying to understand these concepts deeply.
So our mission in this deep dive is to help you do just that.
We want to synthesize all these ideas, right?
Yeah, make sense of all of it.
Because it's one thing to read about all these things.
To kind of get the individual pieces, right?
But it's another thing to really see how they all fit together.
Exactly.
And that's what we're going to try to do today.
Yeah, we want to highlight those key takeaways, those connections, and hopefully spark some aha moments for you.
Right, because that's where the real learning happens, right? When you suddenly see how things connect.
Exactly.
Something clicks.
And we also want to do it in a way that's not overwhelming. There's a lot of technical jargon in machine learning.
Absolutely.
And we want to steer clear of that as much as possible.
We'll explain things in plain English as much as we can.
Yeah, in a way that's intuitive and engaging.
So you can walk away with a solid understanding without, feeling like you need a PhD in math to follow along.
Exactly. So think of this deep dive as your personal guide.
Right. We're going to be your Sherpas through the mountains of machine learning.
We're gonna climb to those peaks of understanding together
and point out all the interesting landmarks along the way.
Absolutely. So where do we want to start with all of this?
Well, given the way your notes are structured, it seems like a natural starting point would be with dimensionality reduction.
Okay, so that was the focus of week one, right?
That's right. Week one was all about principal component analysis, or PCA.
PCA, yeah.
And really what PCA is all about is simplifying data sets.
Okay, so why do we need to simplify data sets?
Well, think about it this way. Imagine you have a data set with, hundreds or even thousands of features.
So a lot of columns in our spreadsheet, right?
Exactly, a lot of columns. And each row might represent a different observation or a data point.
Okay.
Now, trying to visualize or analyze data in such a high-dimensional space can be incredibly difficult.
Just too much information, right?
Too much information, right?
Too many dimensions.
And it can also lead to computational problems. So what PCA does is it tries to find a way to reduce the dimensionality of the data.
Okay, so to go from lots of columns to fewer columns.
Exactly. But to do it in a way that preserves as much of the important information as possible.
Okay, so it's not just randomly throwing away columns.
No, it's very deliberate.
It's about finding the most important ones.
Exactly.
Oh.
And the way it does that is by finding what are called principal components.
Principal components, okay.
Which are essentially new features that are linear combinations of the original features.
Okay, so each of these new columns is somehow derived from the original columns.
That's right. It's like taking all your original ingredients and mixing them together in specific proportions to create new, more informative dishes.
Gotcha.
And these principal components are chosen in such a way that they capture the most variance in the data.
The most variance. Okay, so what does that mean exactly?
So variance is essentially a measure of how spread out the data is.
Okay.
So if you have a feature where all the values are very similar,
Like everyone's height is pretty much the same?
right, then that feature has low variance.
Got it.
But if you have a feature where the values are very different,
Like everyone's income could be wildly different.
exactly, then that feature has high variance.
Okay, so PCA is trying to find those directions in the data, those combinations of features where the data is most spread out.
Exactly.
And those directions become our new principal components.
Right, and by focusing on the directions of highest variance, PCA is essentially finding the most informative aspects of the data.
The stuff that's really telling us something.
Exactly, because the directions with low variance, well, they're not really telling us much.
Gotcha.
They're just kind of noise.
Okay, so to actually do PCA, your notes mention some math, scalars, vectors, matrices.
Those are the building blocks.
Okay, so maybe we should just touch on those briefly.
Okay, so a scalar is just a single number,
Okay.
like the temperature outside.
Got
A vector is an ordered list of numbers. So it could represent something like the coordinates of a point in space.
Okay, so like latitude, longitude, altitude.
Exactly.
Okay.
And a matrix is a rectangular array of numbers.
Like a spreadsheet.
Exactly, like a spreadsheet.
Okay.
And typically, our data sets are organized as matrices, where each row represents a data point and each column represents a feature.
Okay, so understanding how these mathematical objects work is really important for understanding PCA.
Absolutely, because PCA involves operations on these objects like matrix multiplication, finding eigenvalues and eigenvectors, and so on.
Okay, and you also mentioned something about centering the data.
Right. Centering the data is a crucial step in PCA.
And what does that mean exactly?
So centering the data means subtracting the mean of each feature from all the data points.
Okay.
So essentially, you're shifting the data so that it's centered around zero.
Okay, and why is that important?
Well, remember, PCA is all about finding the directions of maximum variance.
Yeah.
And if your data isn't centered, the principal components you find might be influenced by the overall location of the data in space.
So it's like if you're measuring people's heights and everyone is really tall, but you don't center the data.
Right, then the first principal component might just correspond to the average height.
Which isn't really telling us anything interesting.
Exactly.
Right, so by centering the data, we're basically making sure that PCA focuses on the spread of the data around its mean.
Exactly, and not on its absolute position.
Got it.
So from this point on, we'll assume that our data has been centered.
All right, so centered data, check.
Yeah.
What's next?
All right, so once we have our centered data, the next key ingredient is the covariance matrix.
The covariance matrix. Okay, so what does this matrix tell us?
So the covariance matrix is a square matrix.
Okay.
And each entry in the matrix tells us the covariance between two features.
Covariance. Okay. Now, remind me, what exactly is covariance?
So covariance measures how much two features vary together. So if two features tend to increase or decrease together.
Like maybe hours studied in exam score?
Right, exactly.
They tend to go up together.
Then they'll have a positive covariance.
Okay.
But if two features tend to move in opposite directions.
Like maybe number of hours spent watching TV and exam score.
Right, exactly. Then they'll have a negative covariance.
Got it.
And the entries along the diagonal of the covariance matrix.
So the top left to bottom right diagonal.
Yeah, exactly. Those entries represent the variance of each individual feature.
Okay, so it's like how much each feature varies on its own.
That's right.
And this covariance matrix has some special mathematical properties, right?
It does, and those properties are really important for understanding how PCA works.
Okay, so what are those properties?
So first, the covariance matrix is symmetric.
Symmetric, okay.
Which means that the entry in row I, column J, is the same as the entry in row J, column I.
Makes sense, yeah. The relationship between feature A and feature B is the same as the relationship between feature B and feature A.
Exactly.
Okay.
And second, the covariance matrix has what are called non-negative eigenvalues.
Non-negative eigenvalues. All right, now those sound a little technical, maybe.
They do, but they're really important for PCA.
Okay, so can you explain what those are in kind of simple terms?
Yeah, sure. So eigenvalues are essentially a way to measure the magnitude or importance of different directions in the data.
Okay.
And the fact that they're non-negative means that each direction contributes a non-negative amount of variance.
Okay, that makes sense. A direction can't have negative variance?
Exactly.
Okay.
And finally, the eigenvectors of the covariance matrix form an orthonormal basis.
Orthonormal basis. All right, now we're really getting into the jargon here.
I know, but bear with me.
Okay.
So an orthonormal basis is essentially a set of vectors that are all perpendicular to each other,
Okay.
and they have unit length. And what this means for PCA is that the principal components we find, which are the eigenvectors of the covariance matrix,
Right.
they're all pointing in different directions.
Okay, so they're not redundant.
Exactly. They're capturing different aspects of the variance in the data.
Gotcha.
And they form a new coordinate system for our data.
A new set of axes, so to speak.
Okay. Yeah.
Okay, so we've got our center data, we've got our covariance matrix, and we know that its eigenvectors form this special orthonormal basis.
Right.
And those eigenvectors are going to become our principal components.
That's right.
Okay, so how do we actually find those eigenvectors?
Well, that's where the optimization problem comes in.
The optimization problem. Okay.
So PCA is essentially trying to solve two equivalent problems.
Okay.
One is to minimize the reconstruction error,
Reconstruction error.
and the other is to maximize the variance captured.
Okay, so what is reconstruction error?
So imagine you take your original data
Okay.
and you project it onto the principal components.
Okay, so you're basically finding the coordinates of each data point in this new coordinate system defined by the principal components.
Exactly.
Okay.
Now, if you only keep a subset of the principal components,
So like the top 3 principal components, for example.
right, then you're essentially throwing away some information.
Okay.
And you can't perfectly reconstruct the original data from just those 3 principal components.
Right.
The reconstruction error is a measure of how much information you've lost.
Okay, so it's like the difference between the original data and the data you get back after projecting onto those 3 principal components?
Exactly.
Okay.
And the other problem that PCA is trying to solve is to maximize the variance captured.
Okay, and that means what exactly?
So the principal components are ordered by their corresponding eigenvalues.
Right.
And the first principal component, the one with the largest eigenvalue, captures the most variance.
Okay.
The second principal component captures the second most variance, and so on. So by choosing the top k principal components, we're maximizing the amount of variance that's represented in those k dimensions.
Okay, so it's like we're trying to pack as much of the variability of the data into as few dimensions as possible.
Exactly.
And it turns out that these two problems, minimizing reconstruction error and maximizing variance captured, they're actually equivalent.
That's right. They lead to the same solution.
Which is pretty cool.
It is. It's like 2 different ways of looking at the same underlying concept.
Gotcha.
And the solution to both of these problems is to find the eigenvectors of the covariance matrix
Those eigenvectors again, yeah.
and order them by their corresponding eigenvalues.
Okay, so the eigenvectors with the largest eigenvalues, those become our top principal components.
Exactly.
And when we project our data onto those principal components, we're getting a lower dimensional representation of the data,
Right.
but one that still captures most of the important information.
Exactly.
Okay, so how do we decide how many principal components to keep?
That's a great question, and it's a practical consideration that you'll face whenever you're using PCA.
Okay,
So there's no hard and fast rule,
okay.
but a common heuristic is to look at the proportion of variance explained.
Proportion of variance explained. Okay.
So remember that the eigenvalues tell us how much variance each principal component captures.
Right.
So you can calculate the proportion of variance explained by each principal component by dividing its eigenvalue by the sum of all the eigenvalues.
Okay.
And then you can plot this proportion of variance explained as a function of the number of principal components.
Okay.
And often you'll see that the first few principal components explain a large chunk of the variance.
Yeah.
And then the remaining principal components explain less and less.
So it's like diminishing returns.
Exactly, diminishing returns.
Okay.
So a common rule of thumb is to choose the number of principal components that explain a certain percentage of the total variance,
Okay.
like 95% or 99%.
Got it.
So if the first 3 principal components explain 95% of the variance,
Then you could probably just keep those 3 and
Exactly.
throw away the rest.
right, and that would reduce your data from maybe hundreds of dimensions down to just 3 dimensions.
Which is pretty amazing.
It is. It's a really powerful technique for simplifying data.
Okay, so we've got our principal components. We've decided how many to keep.
Right.
Now, how do we actually use them to represent our data in this lower dimensional space?
So that's where projections come in.
Projections. Okay.
So you can think of a projection as the shadow of a data point onto the principal component axis.
Okay.
And there are 2 types of projections that you'll see mentioned: vector projections and scalar projections.
Okay, so what's the difference?
So a vector projection gives you a vector that points from the origin to the point on the principal component axis where the shadow falls.
Okay.
And a scalar projection just gives you the length of that vector.
Okay, so just a single number.
Exactly.
Okay.
And for PCA, We're typically more interested in the scalar projections.
Okay, so those become our new coordinates in this lower dimensional space.
That's right.
Okay, so we've taken our original data, we've found the principal components, we've projected the data onto those components, and we've got this new simplified representation of the data.
Exactly.
And we've done all of this without losing too much information.
Right, because we've kept the principal components that explain most of the variance.
And this has some practical implications, right?
It does. So first, it can make it much easier to visualize the data.
Okay, so instead of having to think about hundreds of dimensions, we can plot the data in 2 or 3 dimensions.
Exactly, and that can reveal patterns that were hidden in the high-dimensional space.
Gotcha.
And second, it can make our machine learning algorithms run faster.
Okay, why is that?
Well, many machine learning algorithms have computational complexity that depends on the number of features.
Okay.
So by reducing the number of features, we can reduce the runtime of these algorithms.
Makes sense.
And finally, PCA can be used for data compression.
Data compression, okay.
So instead of storing all the original features, we can just store the scalar projections onto the top principal components.
Okay, so we're representing the data with fewer numbers.
Exactly.
And that can save storage space.
That's right.
Okay, so PCA is a really versatile technique with lots of applications.
Absolutely. It's one of the most widely used techniques in machine learning and data analysis.
Great. So that was week 1, PCA.
Dimensionality reduction.
Yeah, simplifying data, finding those most important directions.
Right, but PCA is a linear technique.
Okay.
So what happens when we have data that's not linearly separable?
Right, like what if the relationship between the features is more complex?
That's where week 2 comes in.
Week 2, okay.
Beyond linearity.
Beyond linearity. So we're going beyond standard PCA.
Exactly. And there are a couple of key ideas that we need to introduce to address this.
Good question.
First, there's the issue of computational complexity.
Right, you mentioned that earlier.
Yeah, so remember that PCA involves finding the eigenvectors and eigenvalues of the covariance matrix. And the covariance matrix is a D by D matrix.
Where D is the number of features.
Exactly.
Yeah.
Now, if you have a lot of features, say hundreds or thousands,
Okay.
then this covariance matrix can be huge.
Yeah, and calculating its eigenvectors and eigenvalues can take a lot of time and memory.
That's right.
Okay, so what's the solution?
So one solution is to work with the Gram matrix instead.
The Gram matrix.
So the Gram matrix is an N by N matrix.
Where N is the number of data points.
Exactly.
Yeah.
And each entry in the Gram matrix is the dot product of 2 data points.
Dot product, okay.
Yeah, so it's a measure of similarity between those 2 data points.
Okay.
And the key insight is that the eigenvalues and eigenvectors of the Gram matrix are related to the eigenvalues and eigenvectors of the covariance matrix.
Okay, so we can actually get the information we need from the Gram matrix instead of the covariance matrix.
Exactly. And the advantage is that the Gram matrix is smaller when we have more features than data points.
Gotcha, so it's a way to sidestep the computational issues when D is much greater than N.
That's right.
Okay, so that addresses the complexity issue.
Right.
What about the nonlinearity issue?
So to address nonlinearity, we need to introduce the idea of feature transformation.
Feature transformation, okay.
So the basic idea is to transform your original features into a higher dimensional space.
Okay.
Where the data might become linearly separable.
Okay, so we're basically bending the data into a new shape.
Exactly.
Okay, and how do we choose this transformation?
Well, there are many different transformations you could use.
Okay.
But a common example is a polynomial transformation.
Polynomial transformation.
Now imagine you have 2 features, by 1 and by 2.
Okay.
A polynomial transformation of degree 2 would create new features, like by 1 squared, by 2 squared, and by 1 times by 2.
Okay, so we're basically adding all these polynomial terms to our feature set.
Exactly.
And that can create new relationships between the features.
That's right. And these new relationships might be linear, even if the original relationships were not.
Gotcha.
So for example, if your original data points lie in a circle in 2 dimensions,
Okay.
then a polynomial transformation of degree 2 might map those data points onto a plane in 3 dimensions.
Okay, so we're basically unfolding the circle into a straight line.
Exactly.
Okay, but this sounds like it could create a problem.
It can.
Because if we're adding all these new polynomial terms, we're increasing the dimensionality of the data.
That's right.
And we just talked about how high dimensionality can lead to computational problems.
You're exactly right. So we need a way to work in this higher dimensional space without actually having to compute all those extra dimensions.
Okay, and that's where kernels come in.
That's right.
Kernels. Okay. Now, remember you mentioned kernels earlier.
Yeah, so kernels are a really clever trick
Okay.
that allows us to compute the dot product between two data points in a high-dimensional space.
Okay.
Without actually having to explicitly transform the data points into that space.
Okay, so it's like a shortcut.
Exactly. It's a shortcut that saves us a lot of computation.
Okay, so how does it work?
So a kernel function takes two data points as input,
Okay.
and it outputs a single number, which is the dot product of those data points in the high-dimensional space.
Okay.
And the key is that this kernel function only depends on the original features.
So we don't actually have to calculate the transformed features.
Exactly.
Okay. And you mentioned the polynomial kernel earlier.
Yeah, so the polynomial kernel is a common example.
Okay.
And it implicitly computes the dot product as if you had applied a polynomial transformation.
Okay, so it's like we're getting the benefit of the polynomial transformation without having to do the actual transformation.
That's right.
Okay. And there are other kernels besides the polynomial kernel, right?
Yeah, there are many different kernels, and each kernel corresponds to a different type of transformation.
Okay.
Another common kernel is the Gaussian kernel, also known as the radial basis function kernel, and this kernel implicitly maps the data into an infinite dimensional space.
An infinite dimensional space. Wow.
Yeah, it's pretty powerful.
Okay, so we've got these kernels, these magical functions that can compute dot products in high dimensional spaces without actually having to go to those spaces.
Right.
But how do we know that a particular function is a valid kernel?
That's where Mercer's theorem comes in.
Mercer's theorem, okay.
So Mercer's theorem provides a set of conditions that a function must satisfy in order to be a valid kernel.
Okay.
And essentially it says that the kernel function must be symmetric.
Okay, so the kernel of x and y is the same as the kernel of y and x.
Exactly.
Okay.
And it says that the kernel matrix, which is the matrix of all pairwise kernel values between your data points,
Okay.
must be positive semi-definite.
Positive semi-definite. Okay, now that's another one of those technical terms.
I know, but essentially it means that the kernel matrix can be thought of as a covariance matrix in some high-dimensional space.
Okay, so it's like a valid measure of similarity. Okay, so Mercer's theorem gives us a way to check whether a particular function can actually be used as a kernel.
That's right.
Okay, so now we've got all the pieces in place.
Right.
We've got our kernels, we've got Mercer's theorem. How do we put it all together to do PCA in this higher dimensional space?
So that's where kernel PCA comes in.
Kernel PCA.
So kernel PCA is essentially just PCA, but instead of using the covariance matrix of the original features,
Right.
we use the kernel matrix.
Okay, so we're basically swapping out the covariance matrix for the kernel matrix.
Exactly.
Right.
And then we find the eigenvectors and eigenvalues of the kernel matrix.
And those eigenvectors become our principal components in this higher dimensional space.
That's right. And we can then project our data onto those principal components.
Just like we did with standard PCA.
Concise.
But now we're capturing nonlinear relationships.
That's right.
Okay, so kernel PCA allows us to do nonlinear dimensionality reduction.
Exactly.
And it does it efficiently by using kernels.
That's right. Because we don't have to explicitly compute the high-dimensional features.
That's really clever.
It is. It's a very elegant solution.
Okay, so one last thing about kernel PCA.
All right.
In your notes, you mentioned something about kernel centering.
Right. Kernel centering is an important step.
Okay, and why is that?
So remember that in standard PCA, we centered the data before computing the covariance matrix.
Right.
And the reason we did that was to make sure that PCA was focusing on the spread of the data around its mean.
Right, not on its absolute position.
Exactly.
Okay.
Now, in kernel PCA, we're working in this implicit high-dimensional space.
Right.
So we can't actually center the data directly,
Okay.
but we can still achieve the same effect by centering the kernel matrix.
Centering the kernel matrix.
And there's a specific formula for doing this, which you can find in your notes.
Okay.
But the basic idea is to subtract the row means and the column means from the kernel matrix.
Okay.
And then add back the overall mean. And this ensures that the principal components we find correspond to centered data in the high-dimensional space.
Okay, so it's like we're implicitly centering the data in that higher dimensional space.
Exactly.
Okay, so kernel PCA gives us a way to do nonlinear dimensionality reduction efficiently and correctly.
That's right.
That's really powerful.
It is. It's a really useful technique.
Okay, so that covers dimensionality reduction.
Weeks 1 and 2.
Weeks 1 and 2, yeah.
From linear PCA to nonlinear kernel PCA.
Right, so we've gone from simplifying data to simplifying data in more complex ways.
Exactly.
Okay, so what's next?
Well, week 3 takes us into the world of clustering.
Clustering. Okay, so this is something different.
It's a type of unsupervised learning.
Unsupervised learning, okay.
So in supervised learning, we have labeled data.
Right, so we have inputs and we have the corresponding output.
Exactly. And the goal is to learn a function that maps the inputs to the outputs.
Right, like in regression and classification.
Exactly.
Okay.
But in unsupervised learning, we don't have labels.
So we just have the inputs.
That's right.
Okay.
And the goal is to discover patterns in the data without any guidance.
Okay, so clustering is about finding groups of similar data points.
Exactly.
Okay.
And one of the most common clustering algorithms is k-means.
K-means. Okay.
So k-means starts by assuming that there are k clusters in the data.
Okay.
And the goal is to assign each data point to one of these clusters.
Okay.
And we do this in a way that minimizes the sum of squared distances between each data point and the mean of its assigned cluster.
Okay, so we're trying to find clusters that are as tight as possible.
Exactly. And the algorithm works
Iteratively.
So first, we randomly assign each data point to a cluster.
Okay.
Or we can choose k-random data points as initial cluster centers.
Okay.
And then we repeat 2 steps until the cluster assignments no longer change.
Okay.
So in the first step, we update the cluster assignments. So for each data point, we calculate the distance to the mean of each cluster.
Okay.
And we assign the data point to the cluster whose mean is closest.
Gotcha.
And then, in the second step, we update the cluster means.
Okay.
So for each cluster, we calculate the mean of all the data points that are currently assigned to that cluster.
Okay, so we're basically recalculating the center of each cluster.
Exactly.
Okay, and we keep doing this until the cluster assignments stop changing.
That's right. And that means that the algorithm has converged to a solution.
Okay, and that solution is hopefully a good clustering of the data.
Hopefully, but there's no guarantee that it's the best possible clustering.
Okay, why not?
Well, the k-means algorithm can get stuck in local optima.
Local optima, okay.